on properties to this
as well. So start. Okay, there's more in chapter 3 and there's more in chapter 4. Yes. No. So we have to memorize 20 something, I don't know how many letters.
A lot of them are the same. Okay, so the first 4 here are pretty much the same thing. Okay, it's just different by addition, subtraction, multiplication, or division. Okay, a lot of them you can pick out keywords for, and you should already know what they mean. Okay, they're definitions of like right angles. Okay, what is a right angle? It's 90 degrees. Okay, you should know what that is already. Okay, so a lot of them you do already know, but some of them you may not. So the first one we have is the addition property of equality. So that is adding the same number to both sides of an equation. So this is solving algebraically. You add the same number to both sides of an equation. So if I have, we'll do 5x minus 4 is equal to 2x plus 3. Okay, so the addition property of equality would be if I were to take that 5x minus 4 and add 4 to both sides of that equation. Okay, so this plus 4 piece, you're adding the same number to both sides. Okay, it's the addition property of equality. Subtraction property of equality, same thing, just subtracting. Okay, so again, I'll just make up a problem. I'll keep it kind of the same, except this time I'm going to subtract 4 from both sides. Okay. Okay, so that subtraction on both sides of your equation keeps your equation the same. Okay, hence equality. But you are subtracting from both sides of that equation. Okay, same thing with division property of equality, except you're dividing the same number from both sides. Okay, so if I have 5x equals 15, and I would divide both sides by 5. Okay, I'm dividing the same number on both sides of that equal sign, so I'm keeping that problem equal. Okay, we also have the multiplication property of equality. So say I have 1/2 x is equal to 4. Okay, this is multiplying the same number to both sides of your equation. Okay, so you're multiplying that number. So in this case, I would multiply by 2. Okay, so here and here. Okay, to keep that problem equal. Okay, so whatever you do to one side, you do to the other to keep that problem equal. Okay, that's why those first 4 are very similar. It just depends what operation you're doing. Okay, if you're adding, it's the addition property of equality. Subtracting, subtraction property of equality. Okay, and whatever you do one side, you do the other. Questions on those first 4? All right, so the next one then is the distributive property. Okay, so multiply a single term and 2 more terms inside a set of parentheses, or adding together 2 terms with a variable. Okay, so if I have 3 times 4x minus 1, okay, your distributive property, you would take that 3 and distribute to the 4x and to that minus 1 there. Okay, so I would end up with 12x minus 3. Okay, that would be the distributive property. Or if I were to do that in reverse, okay, so say I have, we'll do 3x plus 2x. Okay, both of those terms have an x in it.
So I could take out or factor out an x to get x times the quantity 3 plus 2, okay, which is just 5x. Okay, so that's also considered the distributive property there, when you factor something out like that. Okay, next is substitution property. So if x is equal to y, then x can be substituted in for y in any equation, and y can be substituted in for x in any equation. Okay, so this is where you usually have a number equal to your variable. So if I have x is equal to 7, okay, and I have an equation, okay, then I could replace x with 7. Okay, so I could say 3 times 7 minus 2. So substitution is just replacing what it's equal to. Okay, you're replacing that value with what it's equal to. Okay, those ones I think you've seen before, right? You know how to distribute, you know how to substitute. Okay, questions on those ones? All right, then we have properties of opposites. That's adding a number to its opposite to create a 0. Okay, so if I have any number, I'll just use a, and I add on its opposite, which would be negative a, I would end up with 0. Okay, same thing with any number. So if I had a 4, if I added on negative 4, I would get a 0. That's the property of opposites. You end up with 0. Okay, then I have the identity of addition. Okay, that's the sum of any number, and 0 is the original number. Okay, so if I have, again, any number, I'm going to use a for any number. And if I add 0 onto it, you end up with that same number. Okay, so any number plus 0 is that same number. That is the identity of addition. Okay, we also have an identity of multiplication. That's any number multiplied by 1 is that original number. So these identities just give you that same number that you started with again. Okay, with addition, you get the same number. Same thing with identity of multiplication. You end up with the same number. So any number times 1 is itself. Okay, next we have the definition of subtraction. So that's the taking away of a number from another number. Okay, so if I have a number minus another number, you're just taking away each number. Yep, tough stuff here. So I said, I think you know most of these. The taking away of another number. Do you want another example? No. Okay. All right, so letter K then is the reflexive property. So for every real number x, x is equal to x. So this is when a number equals itself. Okay, or something equals itself. Okay, I could have a equals a, 4 equals 4. Okay, something is equal to itself. Now that comes in handy in chapter 4. I know we're in chapter 2. It comes in handy in chapter 4 when we're doing triangle proofs. So usually we use this if a segment is equal to itself within a triangle. Okay, so segment AB is equal to segment AB. Okay, that's the reflexive property. Okay, we also have the symmetric property. So for all real numbers x and y, if x is equal to y, then y is equal to x. Okay, I can't really make that any easier. So if I have a is equal to b, you can switch them. Then b is equal to a. So sometimes you do have to do this within a proof. If when you're solving down and you get like 4 is equal to x, and it's telling you have to prove that x is equal to 4, you do have to switch it. Okay, and to switch it, you would have to use the symmetric property. Okay? Questions on this page? We're going to start getting into the more complicated ones. All right. Next, we have the transitive property. We use this one a lot. Okay, we use transitive property a lot. So that states if A is equal to B and B is equal to C, then A is equal to C. Okay, so I'm going to do this with some numbers here to make it a little bit easier to understand. So if I have B is equal to 4, okay, and I also know that C is equal to 4, okay, since both of these variables have to equal 4, then they must equal each other because they both equal 4. Okay, so B has to equal C. So if you have something equal to one thing, you have another thing equal to that same thing, then they equal each other. All right. Now, for these ones, this is where I try and pick out key terms in each of these theorems or definitions. Okay, so these ones are might be newer to you. So first one we have the midpoint theorem. So if M is the midpoint of segment AB, then I can say segment AM is congruent to segment MB. So our key word here is midpoint. Okay, we use midpoint. And we know our two smaller segments would be congruent to each other. Okay, so if I have our segment AB, okay, segment AB, and I know M is the midpoint, so that has to be in the middle. Then I can say that segment AM is congruent to segment MB. Okay, so those two smaller segments are equal or congruent. Okay, so that's what the midpoint theorem is saying. So in a proof, if you're ever given that a certain point is the midpoint, okay, you know you have to use the midpoint theorem at some point within that proof to state that these two segments are congruent. Okay, next is the definition of bisect. Okay, we kind of talked about this a little bit before. So that divides into two congruent parts. So if you're bisecting something, it's splitting it into two congruent parts. So I'm going to use an angle as an example here. So if I have this angle, and I have a ray bisecting that angle, it would split that larger angle into two congruent parts here. So this smaller angle here, I'm going to label that as angle 1. And then this smaller angle here, I'll label as 2. I would say that those two angles are equal or congruent. Okay, so I could say angle 1 is congruent to angle 2. Okay, that ray split it into two equal parts. Okay, next is the supplement theorem. Okay, supplement theorem, your key word, okay, key word for supplement theorem is linear pair. Yes, I'm going to start highlighting stuff, so if you have a highlighter, you should use it. Okay, so supplement theorem is if two angles form a linear pair, then they are supplementary angles. Okay, so we talked about what a linear pair was in chapter 1. Okay, in order to use the supplement theorem, they have to form that linear pair. So they have to form a straight line. Okay, it has to form a straight line, and you do need two angles. Okay, so here are my two angles. And again, I'm going to label them 1 and 2. So if I see two angles forming a straight line, I can use the supplement theorem to state that the measure of angle 1 plus the measure of angle 2 would equal 180. Okay, we know when something forms a straight line, you can add the angles together to be 180. And again, keyword is linear pair for supplement theorem. Okay, next we have definition of congruent segments. So that's when you have congruent segments. So AB is congruent to CD. Then you can say AB is equal to CD. Do you remember the difference between the two? Do you remember the difference between the two? If this doesn't have the segment bar or the congruent sign. Okay, this is labeling congruency. Okay, this is talking about the measure. Okay, a specific measure of that segment. Okay, so it would be saying like AB is equal to 4. Okay, you wouldn't use the segment bar to say that it's equal to 4. You write it like this when you have measures. Okay, when you have an actual number measure. So here if I have my segment AB and my segment CD, and I know those are congruent, I can switch to equal measures. Okay, I can go from congruent segments to equal measures. So then I would say that this segment is 4. Okay, it could be 4 units for anything. Okay, if I know that segment is 4, then my other segment would have to be 4 because I knew they were congruent. So their measures have to be equal. Okay, we can do the same thing with angles. So we have definition of congruent angles. So if I have angle A congruent to angle B, okay, then their measures would be equal. Okay, so if I knew that angle A was congruent to angle B, you see that? Okay, and it's labeled like this. Okay, I know those angles are congruent. Now, if I was given that the measure of angle A is 40 degrees, okay, I would know then that the measure of angle B is also 40 degrees because I knew they were congruent. So their measures have to be equal. Okay, so then angle B would also be 40 degrees. Questions on this page? All right, I want you to take a break, so stand up. Yeah. my break.
Yeah, and all the way back.
All right. So I want you to reach really high. Reach really high. Okay, try and touch your toes.
Oh yeah, no. That's not me.
Hey, we're still standing.
What?
Brain break.
It's a brain break. I don't know what else to do. What else do we do? This is a lot of vocabulary. I don't want to like. It's okay. It's okay.
No homework would be an even better break.
The homework's not that long.
Yeah, what is hard homework?
It's just identifying which like
Oh,
theorem or something.
no homework.
No. All right, you guys can sit back down.
On the first page, on the document that you gave us, you know, the one that we right side, the science stuff, you know, how when you open
We
it,
just have to read that.
All right, so coming back together so we can finish this up here. Okay, we are on S. We're almost done. So next we have the definition of perpendicular lines. Okay, so this one, I always remember, okay, two lines. So in order to use the definition of perpendicular lines, you do need two lines to meet at a right angle. Okay, so if you're given two lines, so they say line AB, okay, is perpendicular to line CD. Okay, then they say, then this angle is 90 degrees. You would say it's 90 degrees because of the definition of perpendicular lines. Okay, you had two lines meeting at a right angle. Okay, then we have the definition of a right angle. Okay, there's a lot of right angle stuff going on here. So this is different than the definition of perpendicular lines. This one is talking about the lines. This one is talking about the right angle itself. Okay, so if you have a right angle, then you can say that angle is 90 degrees. Okay, so if I said this angle here, A, is a right angle, then I could say the measure of angle A is equal to 90 degrees. Okay, so definition of a right angle, it is 90 degrees. Okay, we also have definition of complementary angles. Okay, those are two angles whose sum is 90. Okay, so two angles have to add to 90 degrees. So again, those could be adjacent, so I'm going to draw them as adjacent. They don't have to be though. Okay, so if I have two angles here that form a right angle, okay, I'll label one as angle 1, the other is angle 2. Since they form that right angle, I know I could add together their measures. So the measure of angle 1 plus the measure of angle 2 to get 90 degrees. Okay, so two angles that add to 90. Okay, we also have a definition of supplementary angles. Those are two angles whose sum is 180 degrees. Now this is different than the supplement theorem. Okay, you have a supplement theorem and you have definition of supplementary angles. That is why with the supplement theorem, I highlighted linear pair. Okay, that one is specifically a linear pair. This one, it's just two angles that add to 180. So they don't have to form a straight line. Okay, so if I have an angle here, I'll call it angle A, and we'll say it's 100 degrees. Okay, and I have another angle over here. That's angle B. It's 80 degrees. Okay, I know I could add those two measures to get 180. So I could take the measure of angle A plus the measure of angle B to get 180 degrees. Okay, it's just two angles adding to 180. Supplement theorem is different. Okay, everybody mixes that up every single year. Okay, supplement theorem has to do with a linear pair. That is why I highlighted it. All right. Next, we have segment addition postulate. We kind of already went over this in chapter 1. Okay, so given 2 points A and C, a third point B lies on the line segment AC if and only if the distance between the points satisfy the equation. So this is when you had that betweenness of points. So if I have a segment AC and point B is between the two, okay, it doesn't have to be in the center, okay, it's not a midpoint, I can take my smaller segments, so this segment right here, AB, I can add that to this segment BC, okay, and that will equal that entire segment of AC. Okay, so that's what this equation here means. So you can add together your two smaller segments to get your larger. And again, we did do that in chapter 1. Okay, that's what that segment addition postulate is. Okay, we have the same thing with angles. So we have an angle addition postulate as well. So two angles side by side with the same vertices create a new angle whose measure equals the sum of the two original angles. Okay, so if I have an angle here, okay, and I'll just draw in an extra ray. So we have two angles that are adjacent, right? And I'm going to label my two angles, 1 and 2. And this time I'm also going to add points here. So I have point A, B, and C. So with your angle addition postulate, it's very similar to the segment addition postulate. So I can add together the two smaller angles to get the larger angle. Okay, so I can take the measure of angle 1, add the measure of angle 2, okay, to get this larger angle ABC. Okay, so you can add your two smaller to get your larger. Almost done. Questions on this page? Okay, are we doing okay so far still with our different properties? All right, so with the right angle theorem, there's a lot underneath that. Okay, so this again is a right angle one. So before we had perpendicular lines, definition of a right angle, we had complementary angles, and now we have the right angle theorem. Okay, so there's a lot having to do with that 90-degree angle. So you do need to know the difference between all of them. So the right angle theorem, we have perpendicular lines intersect to form 4 right angles. Okay, so if you're given perpendicular lines, they intersect to form those 4 right angles. Okay, that's always true. Now the one that you're going to use the most often with the right angle theorem is that all right angles are congruent to each other. Okay, so all right angles are congruent to each other. So if I was given angle 1 and angle 2 are right angles. Okay, so that's what I was given. Okay, if that's what I'm given, then within my proof, I could say, well, then angle 1 would have to be congruent to angle 2 because of the right angle theorem, because all right angles are congruent to each other. Okay, so I could write that those two were congruent. Okay, we also have that perpendicular lines form congruent adjacent angles. So if I go back to my perpendicular lines here, your two angles are congruent and they are next to each other. Okay, they form those congruent adjacent angles. Okay, the two angles are congruent and supplementary. Okay, then there are right angles. Okay, so if you have your line here, if I know that these two angles are congruent, okay, they have to both be 90 degrees because they have to be a line. The line's 180. Split that in half, has to be 90. Okay, so they have to be congruent and adjacent. Same thing with this one. They form that linear pair, and they're congruent. They have to be right angles. Okay, so this one just has to do everything with your right angle. But again, the most common one you're going to use is this one right here, and that's the one I highlighted. Okay, the last one is the vertical angle theorem. We did talk about what vertical angles were in chapter 1. Okay, that just says vertical angles are always congruent. Okay, this is your freebie within your proof, usually. Okay, so in your proof, you'll always have a picture to look at. So if I have two intersecting lines like this, and I'm talking about different angles, I could always look at that picture and be like, well, I know I have vertical angles in that picture, so those two angles have to be congruent to each other. Okay, so again, I have angle 1 and 2. I could say angle 1 is congruent to angle 2 because of the vertical angle theorem, because they are vertical angles. Okay, questions on those?